Why is reading lines from stdin much slower in C++ than Python? I wanted to compare reading lines of string input from stdin using Python and C++ and was shocked to see my C++ code run an order of magnitude slower than the equivalent Python code. Since my C++ is rusty and I'm not yet an expert Pythonista, please tell me if I'm doing something wrong or if I'm misunderstanding something. TLDR answer. Include the statement, stdin.sync with _studio false or just use fgets instead. TLDR results. Scroll all the way down to the bottom of my question and look at the table. C++ code. Python equivalent. Here are my results. I should note that I tried this both under macOS X v10.6.8, Snow Leopard, and Linux February 6, 2032, Red Hat Linux 6.2. The former is a MacBook Pro, and the latter is a very beefy server, not that this is too pertinent. Tiny benchmark addendum and recap. For completeness, I thought I'd update the read speed for the same file on the same box with the original, synced, C++ code. Again, this is for a 100 meters line file on a fast disk. Here's the comparison, with several solutions/approaches.
TL, Doctor, because of different default settings in C++ requiring more system calls. By default, stdin is synchronized with Studio, which causes it to avoid any input buffering. If you add this to the top of your main, you should see much better performance. Normally, when an input stream is buffered, instead of reading one character at a time, the stream will be read in larger chunks. This reduces the number of system calls, which are typically relatively expensive. However, since the file-based Studio and iostreams often have separate implementations and therefore separate buffers, this could lead to a problem if both were used together. For example, if more input was read by stdin than it actually needed, then the second integer value wouldn't be available for the scan function, which has its own independent buffer. This would lead to unexpected results. To avoid this, by default, streams are synchronized with Studio. One common way to achieve this is to have stdin read each character one at a time as needed using Studio functions. Unfortunately, this introduces a lot of overhead. For small amounts of input, this isn't a big problem, but when you are reading millions of lines, the performance penalty is significant. Fortunately, the library designers decided that you should also be able to disable this feature to get improved performance if you knew what you were doing, so they provided the sync with _studio method. From this link, emphasis added. If the synchronization is turned off, the C++ standard streams are allowed to buffer their I/O independently, which may be considerably faster in some cases.
Just out of curiosity, I've taken a look at what happens under the hood, and I've used truss/strace on each test. C++. Syscall sudo truss c/a.out is lower than in. Python. Syscall sudo truss c/a.py is lower than in.
I'm a few years behind here, but in edit 4/5/6 of the original post, you are using the construction. This is wrong in a couple of different ways. You're actually timing the execution of cat, not your benchmark. The user and sys CPU usage displayed by time are those of cat, not your benchmarked program. Even worse, the real time is also not necessarily accurate. Depending on the implementation of cat and of pipelines in your local OS, it is possible that cat writes a final giant buffer and exits long before the reader process finishes its work. Use of cat is unnecessary and in fact counterproductive. You're adding moving parts. If you were on a sufficiently old system, i.e. with a single CPU and, in certain generations of computers, I/O faster than CPU, the mere fact that cat was running could substantially color the results. You are also subject to whatever input and output buffering and other processing cat may do. This would likely earn you a useless use of cat award if I were Randall Schwartz. A better construction would be. In this statement it is the shell which opens big_file, passing it to your program, well, actually to time, which then executes your program as a subprocess, as an already open file descriptor. 100% of the file reading is strictly the responsibility of the program you're trying to benchmark. This gets you a real reading of its performance without spurious complications. I will mention two possible, but actually wrong, fixes which could also be considered, but I number them differently as these are not things which were wrong in the original post. A. You could fix this by timing only your program. B. Or by timing the entire pipeline. These are wrong for the same reasons as number 2, they're still using cat unnecessarily. I mentioned them for a few reasons. They're more natural for people who aren't entirely comfortable with the I/O redirection facilities of the POSIX shell. There may be cases where cat is needed, for example, the file to be read requires some sort of privilege to access, and you do not want to grant that privilege to the program to be benchmarked. Sudo cat/dev/sda/user/bin/time my_compression_test no output. In practice, on modern machines, the added cat in the pipeline is probably of no real consequence. But I say that last thing with some hesitation. If we examine the last result in edit 5, this claims that cat consumed 74% of the CPU during the test, and indeed 1.34/1.83 is approximately 74%. Perhaps a runoff would have taken only the remaining 49 seconds. Probably not. Cat here had to pay for the read system calls, or equivalent, which transferred the file from disk, actually buffer cache, as well as the pipe writes to deliver them to dubc. The correct test would still have had to do those read calls, only the write to pipe and read from pipe calls would have been saved, and those should be pretty cheap. Still, I predict you would be able to measure the difference between cat file, WCL and WCL is lower than file and find a noticeable, 2-digit percentage, difference. Each of the slower tests will have paid a similar penalty in absolute time, which would however amount to a smaller fraction of its larger total time. In fact, I did some quick tests with a 1.5 GB file of garbage, on a Linux 3.13, Ubuntu 14.04, system, obtaining these results. These are actually best of 3 results, after priming the cache, of course. Notice that the 2 pipeline results claim to have taken more CPU time, user plus sys, than real wall clock time. This is because I'm using the shell, bash s built-in time command, which is cognizant of the pipeline, and I'm on a multi-core machine where separate processes in a pipeline can use separate cores, accumulating CPU time faster than real time. Using /user/bin/time, I see smaller CPU time than real time, showing that it can only time the single pipeline element passed to it on its command line. Also, the shell's output gives milliseconds while /user/bin/time only gives hundredths of a second. So at the efficiency level of WCL, the cat makes a huge difference. 409, 283 equals 1.453 or 45.3% more real time, and 775, 280 equals 2.768, or a whopping 177% more CPU used. On my random, it was there at the time test box. I should add that there is at least one other significant difference between these styles of testing, and I can't say whether it is a benefit or fault. You have to decide this yourself. When you run cat_big_file, /user/bin/time my_program, your program is receiving input from a pipe, at precisely the pace sent by cat, and in chunks no larger than written by cat. When you run /user/bin/time my_program is lower than big_file, your program receives an open file descriptor to the actual file. Your program, or in many cases the I/O libraries of the language in which it was written, may take different actions when presented with a file descriptor referencing a regular file. It may use map2 to map the input file into its address space, instead of using explicit read-to system calls. These differences could have a far larger effect on your benchmark results than the small cost of running the cat binary. Of course, it is an interesting benchmark result if the same program performs significantly differently between the 2 cases. It shows that, indeed, the program or its I/O libraries are doing something interesting, like using map. So in practice it might be good to run the benchmarks both ways, perhaps discounting the cat result by some small factor to forgive the cost of running cat itself.
I reproduced the original result on my computer using G++ on a Mac. Adding the following statements to the C++ version just before the while loop brings it in line with the Python version. Sync_with_studio improved speed to 2 seconds, and setting a larger buffer brought it down to 1 second.